Okay. So last day we finished our few days of being nuclear physicists, and we finished off the lesson yesterday talking about problems with the Rutherford atom. So we can start today obviously with that title. And just a little bit of a check for recall. Hopefully we were paying attention a little bit. My exciting discussion hopefully had some, relevance. Right? All that good stuff. What's wrong with this atom proposed by Rutherford? What should be taking place here? What should be happening to these electrons? Haley? Isn't that exciting? They should be crashing into the nucleus. Why should they be crashing into the nucleus? Why would they be crashing, Atlee? There is an attraction between them, that's correct. But if they're orbiting, why can't they stay out there forever? Why do they ultimately, or why should they ultimately result in them crashing into the nucleus? Chris?
They're losing energy.
And why are they losing energy? And what are they doing as they move? Yeah, they give off light, right? The wiggling charges, right? Wiggling charges produce light. And these electrons should be producing light, and they should be losing energy, and they should be crashing into the nucleus. And they're not. How do we know they're not? Rutherford's experiment proves that the nucleus isn't a neutral, heavy, dense thing, because if all the electrons were sitting on the surface of the nucleus and they canceled out all the charges in the nucleus, it should be a neutral nucleus and not a positively charged nucleus. So Rutherford discovers a positively charged nucleus. Therefore, the electrons must be out there somehow, somewhere. Yep. That's right. Well, no. If as the electrons are crashing, right? As they're going around, they're wiggling. As these things are going around, they're wiggling, which means they're producing these waves, right? And as they crash in faster, the waves get tighter and tighter together, making the light waves high energy. The long waves are low energy, and the medium waves are medium energy. Anyway, those medium waves we would call visible light, all right? We're going to talk more about the spectrum today because it's going to become an important thing. And if the electrons go through all the low, medium, and high waves, we should see this flash of white light. We don't see that. So something's wrong with the behavior of the electrons. They're not behaving the way classical physics states that they should behave. So what do we need? We need new physics. It's that simple. So, Bohr and the quantum atom, problems with the Rutherford model. You can write this down. I've already given you the physics lesson, so let's bring up all of the problems. Now, in our discussion yesterday, I didn't talk about the issue about the positive protons not flying apart. That was also an issue. The reason I didn't mention it is because he had already addressed it. I already told you the great name he gave to the new force that he proposed to hold all the protons in the nucleus. What was that awesome name that he came up with one more time, Haley? The strong force. Excellent. So he proposed the, we have a fire drill. I forgot all about it. That's exciting. We're heading to the right, folks. We're heading to the right. And then out the tech hall. All right? Which means I better stop my recording. It's going to be going on forever.
Oh, sorry.
Okay, so before that little interruption, we were talking about problems with the Rutherford atom. And Haley supplied us with, oops, you want that out here. Haley supplied us with the answer to what Rutherford came up with to solve the problem of the protons not flying everywhere, and that was what we call the nuclear strong force. Strong force is what he used. The nuclear strong force has been mapped out in great detail. Scientists know now that it is a special thing that only acts on short distances. And it must exist again. It's, you know, science and discovery are really, and theory, they're really easy things, right? If the protons don't fly apart, and they should repel each other greatly, then there must be something holding them together. And hence, we theorize the nuclear strong force. Because we observe it, there must be something there. Another problem, negatively charged electrons did not crash into the positively charged nucleus, and they should be. They should be giving up energy in form of light, they should be slowing down, they should be spiraling into the nucleus. It doesn't happen. Also, if they were to spiral into the nucleus, they should be giving off a continuous spectrum. They should be giving off all the colors of the rainbow as that takes place, and it doesn't happen. Before we continue on and talk about how Bohr solved the problem, let's define a few things in here, and let's start by defining what a continuous spectrum is. Am I good to go on? I'm not sure with the interruption. I'm hard to tell who's where. A continuous spectrum is essentially the colors of the rainbow. It's actually even beyond that. It also involves colors that we cannot see, the entire electromagnetic spectrum. But for now, let's just consider the visible part of the spectrum that we can see, the visible part of the light that we can see. Because there are all kinds of invisible light that we cannot see. Ultraviolet, it results in sunburns, right? Infrared is heat. We've already encountered gamma rays. That's the highest of energy of all electromagnetic radiation, of all light. So continuous spectrum is the pattern of color observed when white light is passed through a prism or a spectroscope. And we'll talk a little bit more about spectroscopes and prisms in a moment. And essentially, a prism can separate light out into its colors using something called refraction. You might have learned a little bit about that last year when you did your optics. You would have maybe looked at a prism and how it spreads out the light. Depends on who the teacher was. And when you take that white light and spread out, you get a continuous spectrum. All right? Now, that's not what scientists observed. When scientists, even before they were talking about protons, neutrons, and electrons, which is in the like 1900 and a little bit later, like 1910, 1915. Even before that, scientists were looking at the light that was coming off of gases, that was coming from substances that were electrified. I'll show you some examples in a moment. Let's talk a little bit first then about what a line spectrum is. A line spectrum, could you take the music out, please? A line spectrum is different than a continuous spectrum, and in our experiment on Thursday, we're going to get a chance to look at line spectra. A line spectrum is a pattern of distinct lines, each of which corresponds to a light of a distinct wavelength or color, produced when light consisting of only a few distinct wavelengths passes through a prism or spectroscope. Let's talk about prism or spectroscope. You've seen, like I said, last year, hopefully, and if you haven't, I'm sure you've seen on various science type shows, that if we take a prism, it's usually a triangular prism, right, that is, elongated. You take some white light in that prism, and as the light goes through the prism, the light spreads out into a rainbow of colors. And it doesn't have to be a glass prism that does this. A raindrop works just as fine, and there's all kinds of different, if you have crystal, like if you have something made of crystal in your house, let's say, my wife used to have this little crystal, a little crystal hummingbird, which had this crystal piece in the middle. Crystal's got all those cuts in it, and then it had a little metal wings. Oh, it was pretty. Anyway, and it was stuck to the window with some suction cups. And when the light came through that crystal and bounced around in a certain way, boom, you'd get these rainbows everywhere. You've seen that effect before, is that correct? All right. There's another way in which we can generate rainbows or separate light out into its color, and that's using something called a diffraction grating. Now, we're going to be using some diffraction gratings in the experiment on Thursday, except they're going to be in a tube so that we can have everything around it black so that we can see very carefully what the colors are, all right? For now, I've got these diffraction gratings that are just on these slides, and we can use them as a quick little reference. Let me hand out the diffraction gratings, and I'll tell you right now, well, no, there's two types. There's this one and this one. One is old and one is new, and one is better than the other. I won't tell you which, because I've got a mixture. I'm just going to hand them out. There you go. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. There's 4 right there. And 1, 2, 3, 4. 1, 2, 3, 4, 5. 4. Whoops. Taking this one back. Yeah, there's 4 there. And 1, 2, 3. And I'd hang on to this one. What I want you to do right now, close one eye, if you have the ability to wink. If not, you can use your hand to close that eye. And take a look at the lamps and at the windows and all that good stuff. Now, those people who have the colorful ones are going, whoa. Those people who have the other ones are going, well, yeah, I see some colors, maybe. Could you see some colors with the crappy ones? Just red and green? That's exciting. That's all right. Can you see something with that? Green and blue? Let me take a look at this thing. Here, take that one. Oh, yeah, there you go. Oh, yeah, green and blue and red. That's right. Actually, you know what? These crappy ones are actually better because the other ones are ooh, they're really more for flash. Wow. And that's because of the way the diffraction grating is built. Okay, let's put them aside for a second. Let me do something here first. Let me close the drapes here so we can get some blackness in here. get rid of this guy. Now, a diffraction grating is different than a prism, right? Obviously, there's not a big hunk of glass sitting there. So a diffraction grating works a little differently than a prism. But you'll notice it still creates colors. The way it creates colors has to do with the way it's built. Essentially, that's a little piece of cellophane plastic. And what they've done on the cellophane plastic is they've put a bunch of little lines very close together, all right? And if you take grade 12 university physics, and you should because it's good for your health, it makes you a healthier, better person. Anyway, you will learn how a diffraction grating works and how when light passes through slits, tiny little slits, it also spreads out, very much like it does in the prism, but it actually uses a completely different method. But it spreads the light out. Let me show you kind of how it spreads it out. Here I've got a laser here, and it's not that powerful. I remember being in teachers college, and this guy would tell people that the laser was strong enough to cut right through people, and then he would cut it across the students, and they would all be diving underneath the table. It's hilarious. But it really isn't that strong. But let me just turn on the laser here, and I'll fire it to the back. There it is right there. There you can see it right there on the back. All right. There you go. Of course, Mr. Johnson is going to mess things up for me. No, he's actually going to do a good thing. Put it in front of it. Oh, there you go. Stop. Good job. Get lower. Look at the beam. All right, cool. Now, that particular device is doing exactly what it's doing with the white light, except the laser beam has only one color, all right? One color. And because it has only one color, it's separating that color. Now notice how it's separating it not just left and right, but up and down, which is why when you guys, with the cool ones, look at the light, you see colors going everywhere. And that's because that diffraction grating not only has horizontal lines, but it's got vertical lines as well. Okay, Johnson, get that out of the way. Okay, someone with one that's less exciting. There we go. Now look at there. Look at that one. See which way the dots are now oriented? They're oriented up and down, only in one direction, and they're not as spread out. That means these lines aren't as tight together, and there's only lines heading in one direction, all right? That is essentially what a diffraction grating is. Let me show you one other thing before we get going. Yeah, you guys are having fun with that. That's good. Before we move on and talk about how a diffraction grating is important, all right, guys, get to the diffraction grating out of the way. This is one of these little lasers. It's not very good. You know the little lasers you can buy at the dollar store? They were all the rage about 10 years ago. Students would have them in their pockets all the time. They'd put them on each other's foreheads. It would be funny. And it was great because they were not legal in the schools because actually a laser like this is actually a little stronger than this one here. So they're dangerous. Well, they're not super dangerous. You'd have to hold it in the guy's eye for like 2 minutes in order to cause retinal damage. But they're dangerous enough that we could say, can't have them. If I see them, I confiscate them. It was great. I was confiscating lasers by the handfuls. It was fabulous. So here is some of the stuff that I confiscated because you could buy these neat little things that went on top of them, and then you could push the button, and if you did that, you put that on top, this is what you would get. So let's take a look at this one. Here, I've got one right here. Let's put it in front of the beam here. Let's shine it right. Oh, look at there. Money. Look at that. And if you look carefully, you should be able to see, and this one's not very good, but you should be able to see a repeating dollar sign to the left and right. Can you see a faint repeating dollar sign there? That one's not very good. Let me get another one. All right, let's see what this one does. This one is, oh, happy birthday. Good stuff. And there, see that repeating one on the other side? Right? It's right there. See the dot? And then now it's there? These things are not made by cutouts. You might think that there's a cutout that lets happy birthday through. But in actual fact, if you were to look at this under a microscope, you'd simply see a piece of cellophane. But its lines have been drawn in such a curvy fashion that when it makes its pattern, it's not just a dot, but it's a pattern. It says happy birthday. And that's why it repeats. diffraction gratings will always have repeating patterns, all right? And diffraction gratings simply spread light out. If you could look at that through white light, you'd see rainbows of happy birthday, all right? Let's take a look at one more. Oh, we've already done the money. What do we got? Oh, that's cool. It's a star. This is just for me. I'm playing. Oh, that's unique. Ooh, that's fun. Fun stuff. All right. Oh, there's the happy face. There you go. I'm looking for one in particular. Oh, I've done happy birthday. Look at it. It's going to be the very last one. Oh, look at that. See it? And if you guys might think I'm a harsh, mean teacher, but I care. Right? I care about your future. All right. Okay, that was a long way for that silly little joke there. Okay, so that's what a diffraction grating is. So what were scientists doing with their prisms and diffraction gratings? Well, they weren't looking at lasers, but they were looking at the light that was coming off of electrified gases. Remember, I've already shown you that if you zap gases, they glow, right? Remember, they were zapping everything thanks to Tesla and his Tesla coil. They were zapping to find electrons. Thomson puts the electron in the atom. They were zapping gases. And they were looking at the light that was coming from the gases through a diffraction grating or prism. I am going to zap this neon, and I want you to look at it through the diffraction grating and tell me what colors you see. Not enough light for the wimpy ones. Trade your wimpy one for a good one if somebody's nearby. Okay, I'm switching out. That was neon. I have no idea what the identity of this gas is. It's not labeled. Let's take a look at its colors. Ooh, it's very faint. Yeah, if you've got a crappy one, you're not seeing it. All right, so the screen's giving off too much light. Don't worry about it. No, I'm not going to. The important thing is, though, each gas, scientists discovered, had its own distinct color. Each element that was in the gaseous state, and that doesn't just include the gases, because you can vaporize metals, like you could vaporize mercury and make mercury vapor and put that in the tube and look at it. And you could vaporize zinc, and you could vaporize all kinds of different things. And when they did that, each element had its own distinct pattern. Here on my little chart here, I've got a picture representing the visible spectrum, and then the colors you'd see if it was mercury, and the colors you'd see if it was helium, and the colors you'd see if it was lithium, thallium, cadmium, etc., etc. And the most interesting one was the hydrogen one. The most interesting one was hydrogen for one reason, actually probably more than one reason, for one main reason. Number one, it's the lightest element, but the pattern for hydrogen was very repeating. You'll notice here, these seem to be all over the place, but notice here, the blue, and then the lighter blue, and then the blue-green, and then the red. When they graphed that separation, it made a beautiful curve. There was a perfect relationship between the position of the color and then the next color. And that was interesting. That got scientists thinking, what's going on in the atom to make those colors come out? So it was this line spectrum that really got scientists thinking, how do we explain this? All right? So line spectra are very important. So don't worry about writing this down, but line spectrum of hydrogen gas, you know, if we were to electrify some hydrogen gas, put that into a nice little slit, collimate it, run it through a prism, separate it out, again, we would see this growing pattern between the colors. Okay. So what did Bohr propose, and how then did it take care of some of the problems like line spectra and the problems of Rutherford's atom? Well, let's just bring it up. I'll let you write. And oops, sorry. I'll let you write, and then we'll talk about it in a moment. And as you're writing, I will take the diffraction gratings back. You might think that they might be... I did, actually. I should have maybe handed those out. You might think that it might be cool to steal my diffraction grating because it is awesome. But when you show your friends, they will see you as the science geek you truly are, and then you will be ostracized from any further parties or functions. So it would not be a good idea to bring this out of the science room. Trust me. But don't worry, if you are truly a science geek, when you go to university or college, you will find other science geeks like yourselves, and you will make new friends, better, smarter friends. Just keep that in mind. Some wisdom. Now that first statement, nothing is new. Bohr's model stated that electrons could only exist in discrete energy levels, or orbits, we call them. Orbits actually comes from the idea that Rutherford proposed, that they had to be moving, but we now know that if they're moving, they should be giving off light. So energy levels is better, and actually shells are even better. But we still use the term orbits. Now in the next statement, there's the term, in quotes there, the energy of the electron is said to be quantized. And that's the word that is used when we talk about this idea of quantum mechanics. The word quanta simply means a little discrete piece, all right? Scientists before 1900 felt that energy was continuous. You could have any value for energy, that you could have 1.2 joules or 1.21 joules or 1.22 joules. There was no break in the values of energy that you could have. You could have whatever energy that you needed. Chemists even thought that matter at one point was continuous. Remember when we talked about Democritus, I think I put it in the video, that Aristotle thought that material was continuous or amorphous. So then Dalton said that no, they were made up of little discrete pieces. The atomic theory is actually a type of quantum theory, because instead of having matter being, spread out like you could a bunch of plasticine or something, matter is made up of tiny discrete pieces. That's a quantum theory. It involves little quanta pieces. That's what quantum really stands for, all right? Actually, quantum is singular and quanta is plural, a bunch of little pieces. We even did the same with electricity. Scientists thought that electricity just flowed like a river through a wire, but then Thomson and some other guys discovered the electron, the smallest piece of electricity. That's a quantum theory. it states that you can only have discrete tiny pieces of electricity. This guy, Max Planck, in 1900, found that light was actually made up of tiny discrete pieces, quanta. We call them photons now. And all Bohr did was to say, okay, well, if all of these other things can be made up of little tiny pieces, then maybe the energy that an electron can have can only be made up of tiny discrete pieces of energy. In other words, the electron can exist here, or it can exist here in the next shell, but it can't exist in between. There's only discrete places that it can exist. And that's where our energy levels come from. So all Bohr did was apply this idea of little chunks to the energy found in an atom. All right? So that's why we say the energy is quantized. You could either put the electron in the first orbit there, or in the second orbit there, or the third orbit there, etc., etc. In the mathematics that he used to explain this, because this was all explained mathematically, you might think one night he sat down, not much to do, sitting in his chair, enjoying a beverage maybe, and, I'll put circles around this nucleus, and I think I've got my new atom. By Jove, I think it has nothing to do with that. Very mathematical. He's applying mathematical ideas that were applied to the light and to the electrons and to all this stuff. He's doing all kinds of crazy math. And in the end, when he's done doing the math, the answer to the problem produces these energy levels. In the math he was doing, there was a variable called n, and that variable essentially numbered the energy levels, which you call the first energy level, or the first orbit, and the second energy level, the second orbit. In his theory, he named it the principal quantum number because it's the main number that defines the orbit itself. How big it is, how fast the electrons would be moving if they were, because they really can't, but he could calculate that. So all this stuff came from this. So we call it energy level 1, energy level 2, etc., etc. They were given symbols at first. The first energy level was given K, called the K shell. The second one L, M, N, etc., etc. You might ask, why didn't they start with A instead of K? And it has to do with the experiments that they were doing when they were firing the X-rays at the atoms. I told you a story way back when about, and I might not have, it might have been the afternoon class, but when they discovered X-rays, they started firing them at all the atoms. And different X-rays of different colors came off. Did I tell you guys that story? Yeah. When they got the colors, they would get them in certain values, and they would call them K lines, and they would call them L lines and M lines because they had different values. The scientists who started with K thought maybe that they would discover other colors that came before it. So if he started with A, he couldn't go backwards to Z. So he picked the letter in the middle of the alphabet, just in case they discovered some on the other side. So they started with K in the middle. It turns out that we now know that these X-rays were coming from electrons that were falling to the first orbit, the biggest jump. So then, when they discovered orbits, they said, oh, the K lines were coming because they were landing in number 1. Let's call it the K shell. All right? The ones that were landing in number 2 were the second energy level. We call it the L shell. Now, that's an old way of naming the shells. We very rarely use that anymore, but sometimes we talk about it. All right? And that's where it comes from. So K is the first energy level, L is the second energy level, M is the third energy level, etc., etc. All right? Okay. So he quantized the energy, puts them in shells. The principal quantum number numbers the shells, 1, 2, 3, 4, etc. And we can also use K, L, M, etc., etc. Okay. That's the essential part of Bohr's theory. Here's some of the assumptions that he had to make in order to come up with that theory. And these were the kind of the new ideas that he needed in order to explain the atom, in order to kind of fix the issues with classical physics. Classical physics wasn't able to explain this, so he had to come up with some new rules. The first rule he had to state: an electron doesn't lose energy when it's in an energy level. Even though classical physics says if it's in an orbit, it should be losing energy, Bohr said, we don't see it doing that, so it can't be happening. It's able to exist in an energy level without giving its energy up. It's like it's in a parked state. He actually used the term stationary state, as if it's kind of just hanging out there, even though, according to classical physics, it can't. It should crash, but it does. So again, he's just kind of stating the obvious. It's not crashing, so it can sit there. And you can literally think of the electron as if it's kind of just hanging out there on the orbit, just hanging out there. Higher energy levels are farther from the nucleus. That's really nothing new. Higher levels of gravitational energy are farther from the surface of the Earth. You want to go to a higher energy position on the surface of the Earth, climb Mount Everest, you're on the highest energy position, right? If you slip, you will fall down to a lower position, all right? Electrons will do the same thing. If an electron is in a higher position, it can fall down to a lower position. So the second rule isn't really anything earth-shattering, because it's the same as gravitational energy. If you're at a further orbit, you're further from the nucleus. All right? Thanks. Electrons. An electron cannot exist between orbits, but can jump to orbits of higher and lower energy. Now that's the first kind of idea of the weirdness of quantum mechanics. Quantum mechanics, when you go on to chemistry and study quantum mechanics, very few do. I did. I liked quantum mechanics. I took a second and third year course of quantum mechanics. The rules that govern the tiny, like electrons and atoms, are strange rules. Let me give you an example of what that number 3 stands for. Bohr said you could have an electron here at 1, or you can have the electron here at 2, and it can jump between 1 and 2, but it can't exist between 1 and 2. That would be the same as you climbing the steps to your bedroom at night, climbing each step, but as you go from step 1 to step 2, you don't exist between the 2 steps. It would be like you going from step 1 and poof, poof, step 2, poof, step 3. Obviously that doesn't happen with us, but that's because the physics of the large world is different than the physics of this tiny world. The quantum mechanics rules that. So that's a strange, strange thing. I could explain to you why that works, but I'm quite convinced your heads would explode with too much information. No, can't do it. Nope. I will introduce you to it very slightly next year, and if you continue on in chemistry in second year university, you'll take an introduction to quantum mechanics course, and your head won't explode because we've eased you into it. if you wanted to actually learn more about it, you could look up quantum mechanics. You could look up wave mechanics. You could look up a guy by the name of Louis. It's a French name. I think you properly pronounce it de Broglie or something like that. But since we're in Petrolia, I pronounce it de Broglie. Since Dupuis are Dupies, then this guy's name is de Broglie. Anyway, he kind of introduced these weird ideas on explaining why, right? Actually, Bohr didn't have an answer to why they couldn't exist in between. He was just stating they don't. And de Broglie and then a guy by the name of Edwin Schrödinger came up with ideas that then explained why. But we're not going to get into that. So number 4. So what have we got so far? We got energy levels. We've got further ones. Higher energy levels are further away. And we've also got that they can jump from one energy level to another, but they can't exist in between. That's the fun part. And now some terms. Electrons typically exist closest to the nucleus in the ground state. And that's just like our gravitational analogy. Human beings typically exist closest to the surface of the Earth on the ground, right? If energy is added, the electron can jump to a higher orbit, and that's called an excited state. We say that the atom is excited. You want a human analogy? I suppose if you were to win Lotto 649, you'd get very excited and you would jump very high up off of the ground. There'd be some space between you and the ground. I don't know. I don't know how else to describe that. An excited electron will eventually fall back down to the ground state, just like a jumping Lotto 649 winner will eventually fall back down to the ground. But as the electron drops back down to lower orbits, they release light, and that's where the line spectrum comes from. When an electron falls down, it gives off a burst of light. That's the only way it can release energy. Okay? The size of the jump determines what color it is. So this explains now our line spectrum. If an electron, say in hydrogen, goes from the 3rd to the 2nd energy level, it gives off a red line. Red is low energy. That's just a little tiny jump. But if it goes from the 4th down to the 2nd, it gives off a blue line. That's a bigger jump. That's more energy. If it goes from the 5th down to the 2nd, that's an even higher energy blue, like a violet, a bigger energy jump. If it goes from the 6th down to the 2, it's this last line here. You might ask, what happens if it falls down to the 1? If it falls down to the 1, the jump is so big, it gives off ultraviolet light that we can't see because the jump is so big, it's a higher energy value. So for each different size jump, we get a different color. You get a whole bunch of hydrogen in a tube and you zap it with electricity, the electrons get all excited in a whole bunch of atoms and they fall back down at random times. One falls down now, the other one falls down a little later. So they keep jumping up and falling back down. Every time they fall down, a little bit of light comes out, hits you in the eye. Some of them are falling from the 3rd to the 2nd. Some are falling from the 4th to the 2nd, 5th to the 2nd. So all the time as they're jumping up and down, all these colors are coming out, depending on which one is jumping which. All the colors hit your eye at the same time, and your brain adds those colors up to perceive the color orange for neon, even though you might have saw some red and some green and no blue. So you're seeing all the electron jumps simultaneously. How does an electron get energy? An electron can get energy and go higher up 3 main different ways. All right. Let me again go back to the analogy of you not existing in between the steps. How could you gain energy to climb the steps? Well, you could use your legs, but I like to use kind of a silly analogy. Maybe you come home late one Friday night and your parents are mad at you and you're standing at the bottom of the stairs. They say, go to bed. I told you to come home at 10:30 and it's 12 o'clock. What are you doing? And you give them some lip. Oh man, Dad, you're just so old. You do it. Okay. So what does Dad do? He gives you some energy. Oh yeah? Kicks you in the butt. All right? Gives you some energy. Depending on how hard he kicks you, that's going to determine what step you're going to end up on, right? And because you're an electron, you disappear, right when he hits you, you disappear and then poof, you're on like the 5th step. Oh man, that wasn't hard enough. Right. But then of course you're going to fall down. Boop, you fall down to the ground state. You'd give off some light at that point in time. Then he gets another crack at you, kicks you in the butt. If he kicks you hard enough, he can kick you right to the top of the stairs, right? Make it, go to your room. All right. Now, in an electron, if you kick an electron hard enough, you can actually kick the electron right off of the atom, like gone. It's flying through space. The analogy of that would be kicking you so hard you went right through the roof of the house. And you'd form an ion. That's called ionization. How does it actually work in atoms? You can use electricity. I put it away. You can use electricity. That's exactly what I'm doing when I'm zapping these gases. What's happening is a big stream of electrons is flying through the gas, and every once in a while, one of these electrons that come from the Tesla coil runs into an electron that's in an atom. And what does it do? Boom! Kicks it up to a higher state. And then it keeps on, the other one just keeps on going. So that's like getting kicked in the butt. Zapping a gas excites them by running electrons into other electrons. You can also get electrons to be excited by heat. If you've ever, if you've got one of those old stoves, with the spirally things, the electric ones, you turn on, it starts to glow red, or if you've cut any steel with a torch and it's glowing red, what happens there is adjacent atoms are vibrating against each other so much they literally bump up against each other, and if there's enough energy, the physical bump can cause an electron to jump up. And then it falls back down and gives off some light. All right? So that's number 2. You can heat or you can zap it. Number 3 is you can use light itself. If you were to shine a red beam of light, that exact color, on hydrogen, that would be the exact opposite of when it falls back down, and it'll absorb that light and jump back up. And then it'll fall back down and spit the light back out. But if you could shine that color light onto hydrogen, you could get the electrons to jump up. They'd have to be the perfect color. It's got to be the exact color. If you didn't shine that exact color on it, nothing would happen. It would be like a failed kick. It would result in the electron maybe ending up halfway, but that's against the rules. So it stays where it is, and the light keeps on going. So you've got to hit it with exactly the right color of light to get the electron to jump up. So here's an indication of the 3 different ways in which you can do that. Here, this is in a Bunsen burner flame. We're going to be doing this in our experiment. We're going to take some atoms that are soaked onto a stick. We're going to put the stick in the flame, and it's going to glow. We're going to make the electrons jump with the heat. This is an electric discharge tube. This little graphic here represents a Tesla coil. It's actually a couple of coils. It's a transformer. You don't have to worry about it. But here's one of those tubes, and we're going to zap it with electricity. We're going to look at that too. This, I have no idea what this is representing. Oh, it's an arc lamp. We can use an arc lamp. Oh, that arc lamp is supplying light, right? So this is the one where if you shone light on it, you could get it to jump. An arc lamp is an old piece of equipment. You can tell this is not my newest poster that I have in the room. Stars, all right, give off light by the electrons jumping up and down. Scientists can actually determine what elements exist in stars by separating the light out into their lines, and then looking at that great mixture of lines and separating them out, and then saying, hey, there's some sodium on the surface of the sun. There's some other elements there. We'll talk a little more about that in a moment. Okay. One last little thing here to go along with Bohr's theory. And that has to do with the number of electrons in each of the orbits. And you know what? Don't write the examples down. All right? Just put EG, and I'm going to go through the first 4 or 5 orbits with you. So just put here, right, when you get to that, just put here EG, and then don't mind this. I'll put it off to the side. Remember I said that Bohr didn't just sit there one evening and start drawing circles on a page and invent the Bohr diagram, right? That's the simplest representation of what he came up with. He did mathematics. That's what physicists do. Pages and pages of math. They start with some ideas, and in the end, the mathematics comes up with answers that then have physical meaning. And the orbits are the answers to these big pages of equations. And another answer that came out of all of these equations was an equation that provided the number of electrons that could be in each orbit. And that equation is 2n squared. So the number of electrons in each orbit is 2n squared. This came out of the mathematics. He didn't make it up. He did a whole bunch of math, and this is what came out. So we can do this. How about if n is equal to 1, the first energy level, how many electrons can fit in the first energy level according to his mathematics here? Therefore, number of electrons equals 2. And then I'm going to put a 1 in here. And what's my answer? Sorry? 2. 1 squared is 1, times 2 is 2. You guys knew that, right? You guys have been putting 2 dots in that first orbit since grade 9, I would hope, right? Yes? Oh, sounds good. Let's look at the second energy level. If n, what, you're going to stop now? If n is equal to 2, number of electrons, 2 squared. What's the answer? Yep, 8. 2 squared is 4, times 2, 8. And at this point, you guys are all going, yeah, man, this is good stuff. 2, 8, right? 2 and 8. N equals 3. I'll put it over here. N equals 3. Therefore, the number of electrons equals 2, 3 squared. How many electrons should go in the third energy level? Yep. Yeah, the mathematics gives us 18. 18 electrons. And at this point, you're going, wait a minute. For years, we've been drawing 2, 8, 8. Where's the 18 coming from? And this is where it gets a little complex. It turns out, and again, you don't need to know this for this course, but you do for grade 12. We'll teach this to you in grade 12. But it turns out that in each of these energy levels, there's actually sublevels. There's subshells that exist within the shells. And when you get to higher ones, subshells begin to overlap. And then the numbering gets really goofy. In actual fact, right here in the transition metals, okay, these right here, their electrons are actually going into the third orbit, even though they're in the fourth line. Which means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that's where the shape of the periodic table comes from. It comes from the orbits and how the electrons go into them. How about 4? N equals 4. We'll stop at 4 here for a minute. N equals 4. And therefore, the number of electrons, 2, 4 squared. What is that? Yep, 32. 32 electrons. And now you're going, what the heck? 32 all the way across that thing? That's crazy. You'll never get to 32. But again, like I said, there's an overlap. And it turns out that these guys in here are actually going into the fourth. So if I count across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, let's go down to this guy here. Well, no, let's do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now you might say, oh, Mr. Sanders, what about that guy? That makes 33. These two actually go in this space here, so they don't even count. So all the way across, including these guys down here, 32 comes from that number right there. The shape of our periodic table is not because of periodic trends like Mendeleev thought. but it has everything to do with the orbits and the way the electrons go into them. You don't need to know this stuff that I just mentioned, but you will next year. We'll explain the periodic table completely next year in great detail, all right? And that's where our funny numbers come from. As far as you're concerned, if I'm having you draw Bohr diagrams, 2, 8, 8, and then we stop there because it gets confusing. You don't know enough to actually draw the pictures for these guys. I've seen websites where they just put a whole bunch of dots around them. Wrong. That's not even close to the way we look at the atom. So we stop right there because I need to teach you more quantum mechanics before you can learn more about this. But that's not for this course. Okay, one last little place, and then it's a perfect place to stop here. One last little statement. I've already made this statement orally. I'm just getting you to write it down. Each element has different sized orbits, and therefore its own unique pattern of colors. This addresses why all the lines aren't the same. You might think if they've all got the same orbit, each atom, then why aren't all the colors the same? Why don't all atoms look exactly the same color? And I'm going to just add one statement to this. More protons pulls the orbits in. There's still a fundamental attraction between the electrons and the protons. That's what keeps them in the orbits. As you go from something like hydrogen to helium, and now I'm just listing, lithium to beryllium to boron to carbon to nitrogen, you get the idea. I could go all the way through the periodic table. Each time you move to the next one, you add a proton to the nucleus. That pulls the electron orbits in a little closer. So the orbits for lithium, its first orbit is closer to the nucleus than hydrogen's first orbit because it has more protons and it pulls it closer. Which means when lithium's electrons jump, they make different size jumps. And each size jump gives off its own color, so each element has its unique set of colors because all of their orbits are of different size. And that's very important. That's why when we look at neon being zapped, it's orange, but when we look at another gas, and I can't think of any right now, sodium, if I had a sodium vapor tube, it's very yellow because of the different sized jumps. And because each element has its own size jumps, the line spectrum is a characteristic property. We say it's an intrinsic property. We can use those properties to identify elements. If we gave, and you're going to do that in the experiment. We're going to give you a tube there. It's going to be an unknown. We're not going to have it labeled. You're going to look at the colors, and then you're going to compare it to some other ones that you've already seen, or you can compare it to something like this, and you should be able to identify what that element is in that thing by its colors. All right? And that's all thanks to the Bohr theory with electrons jumping up and down. Okay, that's a good place to stop. Tomorrow we'll talk a little bit about how we can use this theory, and we might start into some ions. Thursday is lab. Friday is atomic theory quiz. We've essentially learned everything that's going to be on the atomic theory quiz, maybe a little bit at the beginning of tomorrow's lesson. All right? And then after the quiz, you'll work on your labs. You'll work on your lab reports. Okay? All right. Good place to end.